So the Heisenberg's indeterminacy principle is also known as Heisenberg's uncertainty principle. And as with most things with chemistry, you have to understand the conceptual basis of Heisenberg's principle as well as how to apply it to problems. So that's exactly what we're going to do in this video. So what does the Heisenberg's indeterminacy principle say? Well, it basically says that you cannot both know two things of an object at any given time. And those two things are the velocity, so the velocity, or the speed, and the position, or the location. Right? It's impossible to know both these two things at any given time. And it turns out the more you know about an object's position, the less you know about its velocity. Right? So they're inversely related. The more you know about the velocity, the less you know about the position. Right? And so this is represented with the following formula. This is something that you should know. Often you'll be given this formula, but you should know what the variables mean and how to apply it. So the formula is delta P times delta X is at least greater than or equal to H over 4 pi. Now, a lot of times delta P, we've seen P before in the de Broglie equation. Oftentimes delta P, which represents your uncertainty in momentum, is represented as mass times velocity. Mass m times delta v. So you'll see two forms of this equation. So let's talk about what each of these variables is. So delta p, as I mentioned, is your uncertainty in momentum. The units of momentum are just the units of mass times velocity, so it's going to be kilograms times meters per second. Delta x represents your uncertainty in position. So just remember that delta here is not representing change, but rather uncertainty. And position is always going to be in meters as its units. Planck's constant, this is probably the third or fourth time we're saying this. 6.63 times 10 to the negative 34 joules per time seconds. Mass is going to be in kilograms as always. And your uncertainty in velocity, which is delta v, is in meters per second. All right, so there's a few things to remember here. Right, so as your uncertainty in delta x increases, your uncertainty in momentum decreases. They're inversely related. And that's the same thing as saying that your uncertainty in velocity, because mass is constant, also decreases. And of course the opposite is also true. So vice versa. As your uncertainty in position decreases, your uncertainty in both the momentum and velocity increase. So conceptually, this is what you should know. You can't know both the velocity and position of any object. The more you know about one, the less you know about the other. So let's apply this to a practice problem. So it says determine the minimum uncertainty in momentum, delta p, and in velocity, delta v, of an electron within an atom of radius 250 nanometers. This is a question that you can definitely see on your midterm or final. All right. So the key thing here is radius of 250 nanometers. You might think that represents your uncertainty in position, delta x, but actually it's not. All right. So here's your radius of an atom. The electron can actually be anywhere within this cloud. And so the uncertainty in position is not represented by r, but rather the diameter. So the diameter of the atom represents delta x, right? So then what do you have to do to r? You just double it. So the radius, 250, so delta x is twice that, or 500. And let's convert this to meters, because that's our standard units. 1 meter is, much larger than a nanometer. And it turns out that 1 nanometer is 10 to the negative 9 meters. All right, so we can write 500 times 10 to the negative 9 meters as our delta x, and we are looking for delta p and delta v. So let's start with delta p. So the first thing I do is identify this as a Heisenberg uncertainty principle problem, and I write the formula. Delta p times delta x is at least h over 4 pi. And then I isolate the variable that I'm looking for. Here it's delta p. So I can say that delta p is at least h over 4 pi times delta x. And I know h, I know 4 pi, and I know delta x, so I can solve. So that's 6.63 times 10 to the negative 34 joules times seconds, divided by 4 pi times my delta x, which is 500 times 10 to the negative 9 meters. I put that in my calculator, and I get 1.05 times 10 to the negative 28 kilograms times meters per second. So notice here that the question asks the minimum uncertainty. That makes sense because the uncertainty has to be at least this value. It's greater than or equal to this. So our delta p is at least 1.05 times 10 to the negative 28, and that's the minimum amount. Now we have to figure out the minimum uncertainty and velocity. Well, we know delta p, and we know that delta p is equal to m delta v. We saw for delta v, that gets us delta v equals delta p over m. We know, we just calculated delta p, uncertainty in momentum, which is 1.05 times 10 to the negative 28 kilograms times meters per second. We divide by our mass, which is given as 9.109 times 10 to the negative 31 kilograms. We put that in our calculator, and we should get 116 meters per second. So that's the uncertainty in velocity, as you can see. So things that are very small, it's often very difficult to determine their position and velocity well, right? And here the uncertainty in velocity is very, very large. 116 meters per second is very large. So this is the type of question you might see on your exam. Sometimes they'll give you, instead of the uncertainty in position, they might give you the uncertainty in velocity and ask you to find the radius of the atom. All right, so it's just a matter of using this equation to the problem that you're given.